135th Audio Engineering Society Convention, held October 17 through 20, 2013 in New York, New York.
Good morning. Welcome to Live Sound Session 9, Intelligibility in Stadiums. A quick reminder, please silence cell phones, pagers, any other devices that may go beep in the night. Today's presentation is going to be from Renato Cipriano and Sergio Molho with Walter Storyk Design Group, Brazil. Renato is a partner for 15 years in the Brazilian office, and he was responsible for the stadium sound system design and implementation in the facilities in Brazil for World Cup and the upcoming Olympics.
Thank you. So my name is Sergio Molho. I'm in charge of the international offices of WSDG, and it was certainly a challenge for our company to get involved in these very substantial and complicated projects in Brazil. When we started to find out that Brazil is going to organize the World Cup and then the Olympics, we put all our energy in trying to find out who is going to be in charge of those projects and who are going to be the key elements on a governmental level, architectural firms, engineering, FIFA, Olympics Committee, and the process to run these projects all over the place was so complex and the place so diverse that it requires all our energy at any level of the company. And we put all the resources from WSDG in terms of engineering, acoustics, physics, systems design, and as a result, we are going to witness what we achieve in terms of performance and in terms of system. So I want to introduce you now to Renato Cipriano, sound engineer, Grammy awarded, and leader of our office. Thank you very much.
Thank you. Hi. Thank you, everybody, for being here today. We're going to talk a little bit about sound systems for these stadiums and some sports arena that we have been involved with. This is not meant to be a technical presentation, but more of an overview of and some sharing of some experience that we had in these projects in the past few years in Brazil. Brazil has become a very big construction site in the past few years with the advent of the World Cup and also for the Olympics. And especially in the pro audio community, there's a lot going on. We have seen many changes, and we are happy that we've been part of these changes. When looking at the title of this presentation, I think we can also replace it by this. We're talking about designing sound systems for spaces that are very hard to deal with. And the reason I say that is because they're usually large spaces. They have very high reverberation times. There are some architectural and structural restrictions and conditions that we have to look at. Usually long distances that we have to cover with the sound system. Many requirements that we're going to take a look at. And an extensive coordination that is required. So I'll make a quick introduction, and then we'll start looking at the requirements, how the process of the design development happens, a little bit about topology, and in between I'm going to show some simulations results that we have done. For those who understand a little bit of soccer history, you should know that in North America, soccer has not been a very popular sport, especially at those times in 1950, when this small stadium called Independência was built. And this is a quote that I got from the web that states that one of the most famous upsets in the FIFA World Cup history was played here in this stadium in 1950 when the United States won over England, and that's not a very common thing to see in soccer. Of course, today this 1950, yes, of course, and today this has changed a lot. So this is one of the stadiums that we have worked on, probably one of the smallest ones that we have, It's inside the city, and it's going to be used for practice games for the Cup. This is another one. This is the second biggest and second most important stadium in the country. It's called Mineirão. It's located in Belo Horizonte, where our office is and where I live in the state of Minas Gerais. As you can see from these old pictures, it's a little hard to believe that 3 years ago you could see this is the sound system that we had. You know, so much has changed. And, after the renovation for FIFA, just this year we had 3 very large concerts happen in this stadium. And another one that we did work on, was a real pleasure, was Maracanã Stadium. For those who have who are familiar with soccer, this is the most famous soccer field in the world, basically because of the history that soccer has happened here in the stadium. It's in Rio. If you have to choose a place to go for the World Cup, this would be the best option that I recommend. Can we get sound here?
Okay, sorry. Both Mineirão and Maracanã stadiums are going to be used for the opening game and the final.
Yep.
So in terms of visibility and in terms of expectations, these are the 2 gems of the World Cup.
Yep, good point. And Maracanã is a good example that they just built everything that was planned, from all disciplines that were involved. We also had a chance to design a few spaces for the Olympics. We're talking about some tennis arenas and aquatic arena. And it's a very large park that involves many other places. And for that reason, we had some requirements for the sound system that I'm going to talk about further on. This is one of the arenas of the Olympics, the aquatic arena, and the 3 tennis arenas. One is a 10,000-seat arena, and then 5,000 and 3,000-seat arena. And we just got the news. That was brand new. Yesterday we just found out that we're also going to be designing these 3 new arenas. One of them is for basketball. The other one's for wrestling and the fights. So how do we start when we have to design for these very hard to deal with spaces? First of all, we're going to have to look at some requirements. These could be as simple as a frequency response for the system, coverage, STI, speech intelligibility. There are some zoning issues that we have to look at, architectural and structural conditions, redundancy for some cases, and of course we're going to have to look at the acoustics. Excuse me. These first requirements are usually documented, and they come with in the beginning of the project we get those requirements. Some stuff we have to look at international standards. Just so you know, in Brazil there is no regulation for sound systems yet. We're just about to create these standards. About the other stuff like zoning, architectural, and acoustics, these will come with each project. Each one has its own demands. Now let's take a quick look at the FIFA requirements. This is a page extracted from their manual. And one of the things they ask for is that the PA system should be capable of addressing sound to different zones inside and outside the stadium. So that's a zoning requirement. It should have some level control because of the noise coming from the crowd. We should be able to adjust the PA level. Another requirement, it's about the power supply. They ask for a 3-hour power in case of a failure. So that's not for us, but that's for the electrical. The system they ask for an STI above 0.55, which is, it's pretty hard to get on a large stadium if you think about those huge spaces that we have to deal with. Regarding the SPL, they ask for 105 dBA. Actually, the minimum should be 100, but we are designed for 105. Frequency response, they talk about 120 hertz up to 5K. But as we all know, we're going to design for a much better, much more extended frequency response for media reproduction. And that's, of course, that's listed on their suggestions. Now, for the Olympics, they have a different approach. And I was actually very surprised that they list a lot of spaces for each project, and they determined the SPL for each one of the areas. They talk about STI, again, for each space, frequency response, and also reverb time, which is kind of new for us, that we have this requirement. So if we look at the ranks where the audience is, the Olympics ask for a 0.45 STI, which is not a very high number, but sometimes it's a little hard to get. We know that intelligibility depends on background noise level, reverb time, and the size of the room. And for these stadiums and arenas, we're usually talking about having a fair STI value in that scale, which would be in between 0.45 and 0.6. Sometimes we can get a little higher. It really depends on the type of arena that we're dealing with. And if we look at these formulas of the percentage of our cons, we can see that the reverb time has a big influence in the STI, and also the distance that we place the sources, the directivity, and also it is affected by distortion on the system. So we got to be careful about that. Excuse me. Often we see that these arenas have very high RT60 and the long distance and the limitations for acoustical treatments. Sometimes we just cannot use the walls on the arenas because they're usually taken for other stuff. And we may have only the ceiling to deal with, and sometimes that's not even possible. So the good news about this is that we have good simulation tools today, and we can predict results with great accuracy. So that's part of the work that we do. We always try to simulate these rooms. We run a few passes until we get the best solution.
Renato, one question. Understanding that the FIFA regulations or requirements were a little vague in comparison with the Olympic Committee, how you deal with the regulations of FIFA and who was in charge of that?
Well, yeah, we had a long talk. There was a person responsible, but honestly, they were much more concerned about video reproduction because of the media and the propaganda involved. But I do know that FIFA does have a lot of, they do the tests in the field, and they really test what they have specified for the systems.
Okay. And regarding the Olympic Committee, there's an audio chief or someone in charge?
There is a person. In Brazil, they have named one guy that he looks at all the designs involved, and he's the one that's going to decide if the design is fulfilling their requirements. And there's also a production guy that will take a look at this, and he's going to guide us to some decisions. And I'm going to show you two examples here of what we have to change to fulfill those requirements.
Thank you.
So in the design developments, after we look at the requirements, we take the architectural plans and we start modeling and creating the computer model that we're going to use for the simulations. Then we're going to choose the technology that we're going to use, what kind of speakers, point sources, line arrays, etc. We select equipment, and then we look at the results. And that's an interactive process. After looking at the results, sometimes we have to go back to the system technology. Here's one example of a system that we designed for the small tennis arena. It's a 5,000-seat arena. It's an open space. They have this roof structure in one end, in one corner. And we have defined a system that seemed to be an elegant solution for this arena, which was a line array with 8 speakers, with 2 side fields, 2 point sources on each side. If you look in plan, this would be how it would distribute sound for the audience. With this setup, we got a very good coverage for all frequencies, and we got a very, very high STI readings. But there was an issue with this. Using just a line array and 2 side fields, we got only 3 zones that we can control. And later on in the project, when we sent this for their approval, the committee said this is not happening. And the reason is that they need more control. There are some broadcasts going on. There are some people that sit by the field and they have their own microphones, and they want the sound system to be controlled so that it doesn't affect their transmission. So we were told that we need to create as many zones as we can for this system. So the second option that we had to go back to was to create point sources. If we look in plan, we would have the blue dots would be 1 speaker each, and the red dots would be a cluster with 2 speakers. They're all point sources. Using this option, we have, again, a very good sound pressure coverage and a very, very good STI also. This graph on the lower portion shows the direct to reverberant relation, and that shows us that we have more direct sound arriving at the listener. So this is also a good solution, and it does fulfill the requirements regarding the zoning control.
Renato, when in the process you find out about these zoning issues and the reasons, basically the broadcast and the television show production reasons, when in the process you find out the requirement?
That was a problem that we had. I wish this information was listed on the requirements, and it wasn't. And we were hired before in the process, before this guy who runs the show showed up. And when he saw the design, he said, yeah, this is not happening, not with me, so because I need control of this zoning. So we were almost done with the system design, and then we had to go back and do it all over again. There's another example of this that happened also for the other arena, which was the aquatic. We built the model. In the beginning, we had this square here in the center, which would be a video cube, 4 large video screens. So when we had to discuss our options, we decided to go with a line array solution with 4 line arrays around the video cube, which would be a very elegant solution, if I may say that. And we would need 2 speakers below the cube for these areas to cover these 2 areas here at the bottom. This is our our SPL coverage that shows a very, very uniform reading. But again, we had this issue about the zoning. We could only have 4 large zones and 2 small zones at the bottom. So this was not approved, and unfortunately was almost at the end of the process. So we had to create a different solution different solution to fulfill this zoning criteria. Then we go back to the system technology, and we now specified clusters of point sources at the roof. They are following this catwalk designed by the structural engineer. And we have not only those, but after simulating the results, we found out that there was an acoustic shadow here under the upper rank, where we had only two lines of seats that were not covered and did not have enough STI. Remember, the other system was in the center, so we didn't have that issue. So now we had to add 100 of these small speakers to compensate for this. So it's a complete different system. And now we have the results, the SPL, which are very uniform again, and STI, again, a very good reading. We're talking about 0.6 STI. Just a comparison here with the point source and the line array. We see that the line array could have provided a little bit better result. And now we have the zoning fulfilled as determined by our client.
Renato, can you illustrate us regarding the modeling process and what kind of software do you use to perform that modeling and simulations? It's mentioned on the slides, but
we use the CAT Acoustics. It's a software that we strongly rely on. We have used other systems too, but recently most of the work is done using CAT. Let me just go back to show you the 3D model. So when you see these drawings, they represent what the input that we have in the system. The green areas show the audience. They have we're talking about 80% occupancy, and these people, they have their own absorption coefficient that we have to introduce to the model. We obviously have the roof with its acoustical characteristics. This orange area is an area for broadcast also, so we have a lower density of people here that we always also have to consider. And the field of play, where the pool is. So each color here represents a different acoustical characteristic of the model. So I would like to show now an example, a comparison of an auralization example of these two systems. For those who are not familiar with, the auralization is the capacity of listening to the sound system in this model. I just wanted to point out that these simulations were meant to be heard over headphones, but just for an example, I'm going to show you through these speakers here. But you can get the idea. Hold on, let me just get the first slide. So this first slide shows the option of this point source system distributed in the roof.
Soundcheck is the definitive audio test disc. It contains practical material compiled as a result of careful research and investigation into the needs of studio engineers, audio technicians, serious audiophiles, record producers, and musicians. The disc has been designed not only to help assess the technical performance of a wide range of sound recording and reproduction equipment, but also...
So, I'm sorry, for some reason this was paging. Let me go back here. I was on page 4, which was the point source example. I would like to start with the line array example. So, we are here. Oops. Sorry. We're here looking from the upper rank as if we were sitting here, facing the PA system in this position, and this is how the line array system would sound like.
Soundcheck is the definitive audio test disc. It contains practical material compiled as a result of careful research and investigation into the needs of studio engineers, audio technicians, serious audiophiles, record...
So you see you have a better presence than compared to the point source system.
Soundcheck is the definitive audio test disc. It contains practical material compiled as a result of careful...
Here you can hear more reverberation from the room. That's pretty obvious. But if you move to a different location, now you're a little bit further away from the point source. So you would expect here to hear more reverb from the arena.
Soundcheck is the definitive audio test disc. It contains practical material compiled as a result of careful research and investigation.
Still a little bit better than the other one, but if we go to the point source in this position, now we are close to the speaker, and then it should sound different.
Soundcheck is the definitive audio test disc. It contains practical material compiled as a result of careful research and investigation into the needs of studio engineers, audio technicians, serious audiophiles, record producers, and musicians.
We're still having a lot of reverberation from the room, but it sounds a little bit more clear. So, at the end of the day, we do what we have to do. In this case, we had to fulfill the requirements, which was more about the zoning issue that we had to deal with. A little bit about acoustics. We did have to check, and whenever we run these simulations, we can have the readings from this room. We're talking about around 2.5 reverb time in the low frequency, and that's about the limit that they specify. We had a discussion about reducing these levels of reverberation. That would take a lot of money, and the only space we had available was the roof. And when we simulated the treatments at the roof, we found out that those values at the low frequency wouldn't change much. So that it didn't mean much to spend that money in order to reduce a little bit of the mid-frequency, which, of course, it would improve the intelligibility, but we were already above the limits, the requirements, so we were in good shape. Here's just a comparison of reverb times of the other arenas. The aquatic was in the 2.5 range. The tennis one was 1.9, which is pretty good for this kind of arena. And of course, the open areas, which are the smaller tennis courts, have a very low reverb time, so we didn't have to worry about those. But if you look at the stadiums, we're talking about very high levels of reverb time, and that we have to be careful.
Renato,
sorry?
during the design process, those parameters were discussed with the architect and the decision makers. What was their opinion regarding this? Do they understand what this means?
Yes, that graph was shown, and that was the discussion. We did come up with a cost for that solution of bringing down the reverb time, and by seeing those numbers, there was a decision to be made, which was, are we going to spend this money to reduce, 0.2 seconds on the reverb time and increasing the intelligibility about this much, which is already good. So that it wasn't too hard to make that decision.
But it's good to have the data. That was the...
Oh, yeah, sure. And then we had to present that because we do have those requirements to take a look at. Now, this is the large tennis arena. In this case, we didn't have to choose much of the systems because we did have an architectural condition, which was the roof structure. When they designed the room, they conceived this ring at the roof where we should place our speakers. So we came up with these clusters in blue, which are the main clusters. We had some downfills for that portion of the ranks that are close to the field of play. and the field of play itself, which is also a requirement that we have to have sound there. So if we look at the section of this arena, we'll see that they have planned to have this structure here to hold the sound system. So a line array wouldn't be an option here at all. And if you look close, this is what the architects drew for us, showing what they wanted the sound system to be like. But of course, if you look at that, you see that it's not only too small, but you have only one speaker, and we can't do our job with that speaker. So when we started simulating the system, we found out that we need one speaker to cover the upper rank, one to shoot sound down, and the other one for those areas close to the field of play. And we had a little concern here that we have sound coming from behind these people, these guys that are sitting here. Of course, it's not a very comfortable situation, but it's the only option we had. The only other thing we could think of would be hanging speakers in the center of the arena, which would be very expensive, and they didn't want to do it. Just remember that we had the field of play also to cover, so we're using 2 speakers on each end of the field of play. So when we look at the structure and the final solutions, we're going to see that we had to go beyond the limits that the architects provided us. And they were not super happy with the solution because we're getting out of this space that they had determined. But that's really what we need. There's not too much we can do about it. And we did get a very good STI rating, very uniform in all of the spaces. Also coverage, we're talking about 117 dBc all around again, very uniform. If you look at the direct over the reverberant sound, we see that we have much more of direct sound going on. So it's a very consistent system. So after we define all these electroacoustic things, we start interaction with the architectural program, and we look at the other disciplines. So talking about topology, we're going to have to choose our amp rooms. We're going to define the distribution path those cables are going to run. Where the technical rooms are, sometimes they are the same as the amp rooms, depending on the arena. We need a control room, of course. Here's an example of the Maracanã Stadium where we had this ring at the roof, distributing a lot of clusters around, and we had this distribution path here that we used to bring the cables from the technical rooms that were located at the levels below. Remember, we do have a lot of ceiling speakers. In this stadium, we had 2,600 in ceiling and wall speakers for the evacuation systems. So we do have a lot of cables going around, a lot of distances to cover, and that's pretty much how we determine the best distribution network that we're going to use. Now, for the control room, we have some requirements of space. We have our CMR that also is connected to the other amp racks. Some of the amps that distribute for the internal sound system are also located here. There are some acoustical requirements. We need a view of the field. This may sound a little strange, but we did get one drawing from the architects that the control room could not see the field. So, and you know, it's kind of strange that you have an audio and video control room, and they don't pay attention to that. But of course,
What a surprise!
Yeah. So this is a picture that shows the view from the control room. So you can see at least 2 of the large screens that we have also designed. We have 4 of these very large video screens. And just a brief parenthesis here to show that we did have to take care of the acoustics in many places in this stadium. We're talking about complete floating systems, just like studio constructions that we do all the time. And we specified those for studio control rooms, for TV studios, and for the control room, as well as for an auditorium that we have inside the stadium. And these are very low-level rooms. We're talking about NC20, NC25 for some of them. So we did have to be concerned about the acoustics here.
This came up from the FIFA requirements?
Yes. Well, it was a mix. It was a mix of FIFA requirements and our Brazilian standards,
okay,
regulations that we had to use. I'm going to quickly jump here to an example, a report that we did for the Maracanã Stadium, which I think it's very interesting when we started the design process. We were choosing, we had this doubt of choosing a point source system versus a line array system for the stadium. So we simulated both systems. In this case, we started with system A, which was a point source. And when we created the model, we started placing two of the clusters closer together and this other one a little bit further away. And the reason why is when we start the simulation, it's a very long process. It's a lot of work involved. And before we go crazy distributing all of the other clusters, we need to find out if these distances are correct. So we chose two different distances to start with. So this would be the configuration for each system. We have the catwalk, and we have one point source pointing to the upper rank, the other one to the lower rank, and one pointed down. These two on the sides are long throw, and the other one is a short throw, shooting sound down. So this is the first pass of the simulation that shows the sound pressure distribution from both systems. You can see that for the clusters that are spaced further away, we have a 4 dB drop in the pressure. So that would not be an option. We would have to go with the closer clusters. Same here for STI. You can see the difference when we are further away. Much better coverage for the close clusters. Now we look at the detailed information for the STI readings. And we are in very good shape here. We're talking about, very little areas below 0.5, which is a very good reading for this first pass. Now, we tried a line array solution here. We had to check to see if it was going to be a better option. So we placed same thing again, two clusters close together, one further away. Now we do have one cluster that's aiming for the lower ranks and the other clusters to the upper ranks, which would be a delay cluster. So this is more or less what it would look like. One thing we found out is that these, by using these two clusters, a smaller line array, we would not get a very good coverage on the upper ranks because they would be too close to the audience. In this case here, where we have the bigger line arrays, they are far from the audience, so they give us a much better result. So these line arrays here at the top, they could be replaced by point sources. So if we were to go in that direction, we decided that we should really have the point source as the first option. And this would be the reading for using two line arrays. Now here we have a comparison of both systems. System A which is the point source, and system B, which is the two-line arrays. You can see that system A was a much better option. And this is the final installation. So this picture was taken about a month ago. Unfortunately, I was expecting to bring you the results for this system, but we had a surprise. And there was a story about these the speakers. When we finished the design, by the time it gets to the installation, there's very, very common that they change the solutions that we had specified. In this case, they changed the speakers, the speaker brand and models. And we did look at those specs, and we did recommend that they use 3-inch drivers for the high frequencies, but they have chosen to use 2-inch drivers. And after the Confederation Cup, we were about to go there and make the measurements, and we got information that 17 of these drivers were blown during the first use. So we could not, very unfortunately, I could not go there and make the readings. So they are replacing those drivers, and we hope to get that comparison between the simulation and the final test very soon.
Renato, during the design phase of the project, do you receive any particular recommendation in terms of brands that you can or can't use, or any particular Brazilian recommendation, like use Brazilian components instead of importing materials?
Yeah, they tried. They tried that. In the very early in the process, they were talking about only using Brazilian products, but it wouldn't be possible. We don't have enough good products. We do have some good stuff, but at the end they decided we could use anything we wanted. In our end, it doesn't really matter what manufacturer we use, as long as it does the work. And like it happened on this stadium, they replaced and now they're gonna just fix these drivers, and it seems to be working.
Now that most of your designs were installed, in what percentage they really perform what you designed?
That's a good question. I think we're in the 80% range, which is good.
Acceptable.
Yeah, it's pretty good for Latin America. I don't know, maybe for the Olympics we're going to go a little bit above that range. Here's just a quick example of what kind of things that we faced during the process of the design. We came up with this solution of having the clusters here at the catwalk, right under the catwalk. And one day we got this email from the architect saying they wanted the speakers here because they didn't like to see it. So it's like, what are we talking about? We can't look at the picture. Think about placing these speakers right here. We wouldn't hear anything, or maybe a little bit of low frequency. Anyway, we do see that stuff happening, and that sometimes that becomes a nightmare for us. We have to explain, and one thing I learned in these projects, we have to educate our client as fast as possible in the beginning before they come with these crazy ideas. Just another quick report that I think it's very interesting. It was for the Mineirão Stadium. It's the second biggest one. We did have to do the same process of choosing the best system. In this case, we started by looking at this option of having 2 clusters to cover a very, very wide range here. We have type A, which is the green area. That would be very wide, but a short throw, and the type B with a long throw. And, different locations of the stadium, we had different situations here to deal with. And the first study we did was to use a big line array at the roof, and we found out that by having such a big system, we were talking about covering a 90-degree angle, and this line array would start working as a point source system. And it wouldn't give us the best coverage that we needed. And we also would have to deal with a mechanical issue of too much weight to be placed at the roof, and they did not allow for that. Excuse me. So we started studying two options, two different systems. Like I said, we don't care about the brand. We just pick our options and start studying them. In this case, 2-point source systems. They had different angles. That's the reason for choosing them. And we started simulating the lower ranks, and then another cluster for the upper ranks. And now the two combined solutions. We can see that this option here, with a different dispersion angle, would give us a better coverage. So that's the one that we chose. And here, this is also a FIFA requirement. We have to cover the field. So we did use 4 bigger speakers here at the roof. You can see the pressure distribution, which is very uniform again. STI here is very well. It's above the limits that FIFA requires, which is 0.55. We made sure that no seat had STI below that number. And for that, we had to use these speakers under the balcony to compensate for the acoustic shadow that we had in the stadium. Now, one particular thing that we found out in this study that I would like to show you, here we have the stadium in construction. Now it's a picture after it was completed. And this is when we first started. That was 3 years ago. This is how it looked like. And I had a chance to be there in one day, very quiet day with very little people. And we made some noise there, and I could make some field observations and find out that we did have an issue with this concrete wall around the stadium. By being there and making some noise and listening to it, we found out that most of the sound that goes in this area, and if you think about any speaker that would shoot sound in this location, it bounces back and it gets stuck inside the arena. So after that, we did run some simulations, and we confirmed, if you look in this graph here below, we confirmed that, we have these red lines, which are the direct sound from all the sources, and we found out that we have very nasty reflections here from this ring, and they happen, after 0.5 seconds. And those reflections, which were first-order reflections, they would not allow us to get enough intelligibility for the sound system. So we defined an acoustical treatment for this ring, and here we could, by installing absorption in this ring, we could reduce the reverb time from at 1K from 3.6 to 3.1, which was enough to give us sufficient STI. So if you look here, we had the minimum here 0.46, and we did want to not to have anything below 0.5 for the minimum reading. And we had the average of 0.61, which is pretty good for such a large stadium. And this is the solution that we came up with. We had to use a metal perforated plate so that it would, contain any vandalism that could happen here. And behind it, we had the treatment. This is the absorption curve that we got, and that's how we managed to have this STI covered. Another example I would like to show you here. Yes.
Of course, the same acoustic treatment will allow a better performance when you have a live show, not even a soccer game, when you have a live performance.
Oh, of course, yes. I had a chance to see a rock concert, which I actually recorded for a local band in Brazil, and that performance happened right before. It was the last thing they used in that stadium before the renovation. So it was a rock concert, and I could be there to record it. And after that, I came back on this Paul McCartney event, and you could see there was a significant change in the room acoustics. And, of course, it would sound much better after this renovation. Here, I would like to conclude the presentation showing you that a small system that we compared the simulations with the field tests. And that's something we do all the time, of course, and that's how we learned if we're doing the right thing or not. This is a very small arena in Switzerland. It's called Thun Arena. And you can see that the distances from the sources are very, pretty close. No, it's not a big field, so it shouldn't be too hard to define this system. So we have these speakers at the roof. These are the simulations that we have. And here, this graph shows the prediction versus the field measurements. You can look at the scale here on the left. You're going to see that, the red color shows STI above 65. And these plots that you see now on screen, I hope you can read that. It shows, using colors, the comparison from the original simulation and the field tests. There's some strange regions here. You see in the top, the color is a little bit different. But for the most part, it's very uniform. So these models, these readings, they really depend on how well you define your computer model, how detailed your information is. Because, for the speakers, for the system, we do have their data that we can use. And the biggest variable here is the acoustics of the space. So if you model it well and if you had used the right settings, you should get very precise readings. And we do rely on these models to create our systems. So that's pretty much what I wanted to show you today. Just a few conclusions that we learned. The great majority of the large spaces, they demand very high levels of intelligibility amongst all the stuffs. And the proper use of simulation tools has become very critical for these sound systems. It's something we do have available. There's no reason we shouldn't use these simulations. And I highlight here the word proper, and that refers to creating the best model that you can do, by inserting the right settings. The implementation of these systems, they can only succeed after a lot of collaboration and coordination with the other disciplines that are involved in the process. There's a lot going on with the architecture that we have to deal with. And this is, it's pretty obvious, but sometimes we not see this happening. I guess that would be a good question when you talked about if they are installing what is planned. I guess the best question, are they tuning these systems the way they should be tuned? Because that's very critical for achieving the results that we're expecting. And another thing that we learned, that we're not as important as we think we are when in such big projects. They really don't care about us. We're just the sound guys. But if things goes wrong, they will need us to evacuate the system, and that can only happen if they can really hear us. Well, thank you very much. I'd like to take this time to answer some questions that you may have here. Thank you.